All right, how is everybody this morning? Good. All right, sorry we got off to a little bit of a late start here. I got caught up in a discussion. But thank you for coming. So today we're going to start with a review of Kirchhoff's laws. Remember we talked about Kirchhoff's laws last time. We said that there were two laws. Anybody remember one of Kirchhoff's laws? Yeah. Just the name.
KCL?
Yep, KCL, Kirchhoff's current law. And what was the other one?
KVL?
Yeah, KVL, Kirchhoff's voltage law. So we'll talk about both of those, just a quick refresher, and then we'll remind ourselves about voltage dividers. And then we'll go on to our main topic for today, which is Watt's law. So Watt's law is really more of a definition than a law, okay? So it's really the definition of power. So first of all, we'll talk a little bit about what is power, and then why is it important in electronics, and then we'll just go over what Watt's law actually is. So there's one main form, but we can actually write it in several different ways. And then what does it mean? And then we're going to go on to a different topic today also, which is rounding. So rounding is the process of taking a number that might have a lot of decimals and then shortening it to only a few. Or taking a really large number that might have a lot of digits and just keeping the first several digits, okay? So it seems like it shouldn't be that complicated, but there are a couple of fine points that are important to understand, okay? So we'll do that, and then we'll go on to a preview of today's lab. And for homework, I'd like you to work on the Watt's law core competency and the rounding core competency. Remember, these core competencies are those quizzes that you take on Canvas, and you can take them as many times as you want, and you get to keep the highest score, okay? So please work on those two. You should have enough information to complete those after today's lecture. So any questions before we get going? All right. All right, then let's start with a quick review of Kirchhoff's laws. So we said that there were two Kirchhoff's laws. The first one was Kirchhoff's current law, KCL. So can anybody remember what Kirchhoff's current law actually says?
As much current that comes to a node,
Yep.
that much goes out from the...
Exactly. So if we have a circuit here and we have a node in that circuit, remember a node is just any point on that circuit, then Kirchhoff's current law says that the current flowing into the node has to be equal to the current flowing out. So if we have, say, 10 milliamps flowing in there and 5 milliamps flowing in from that direction, and we know that we have, say, 12 milliamps flowing out that way, then how much current would be flowing out in that direction? 3, exactly. Because we have 15 flowing in, we better have 15 flowing out. So we'd have 3 milliamps flowing out that way. So any questions about what Kirchhoff's current law says or how we figured this out? Okay. Yeah, so another way to think about it is that current does not build up at any one point in the circuit. Any current that flows into a point just keeps on flowing out. Okay? So that's Kirchhoff's current law. And then the next law was Kirchhoff's voltage law. Or KVL for short. So Kirchhoff's voltage law said that if we have a circuit, well, yeah, what did it say? Anybody remember?
Total of the voltage that flows in a loop is equal to 0.
Yeah, exactly. So if we add up all of the voltages around a loop, they have to add up to 0. So say we have a 12 volt power supply here, and we've got a circuit like this. And let's say we had, somebody told us that we have 2 volts there. We could use Kirchhoff's voltage law to figure out the voltages for the other elements in the circuit. So for instance, if we wanted to figure out this voltage over here, we could make a loop in our circuit. We could start this loop there, go around there like that. And in order to do this, we need to know which side of our power supplies and which side of our voltages are positive and negative. So, all right, so if we want to use Kirchhoff's voltage law here, we could start here and go around this loop. So we could call this right here the unknown voltage. And so if we're starting here, we would say we're going up by this unknown voltage. So we would have plus this unknown voltage. And then we come over here and we go down by 2 volts. So minus 2 volts. And then what does that equal? What does Kirchhoff's voltage law say that all the voltages have to add up to? Huh? Yeah, 0. So if we add those together, they have to be equal to 0 volts. Okay? So something minus 2 volts equals 0 volts. So this unknown thing, our unknown voltage has to be 2 volts. Okay? So we could use that to figure out that voltage. Any questions about that? Okay, so now we could also kind of see that by looking at it, because we can see that these 2 resistors are in parallel, and we know that the voltage should be the same for all elements that are in parallel. So we could kind of see that by looking at it, but Kirchhoff's voltage law is a formal way of saying that. Right? So we figured out that voltage, and now we could figure out the voltage for the whole circuit as well. So we could make another loop. We could start here. We could use this to figure out the voltage for this resistor up here. So we could start there, and then go up around here, and then maybe come down this side, and then end up back where we started there. And if we do that, then we can use Kirchhoff's voltage law again. So we would start here, and then we would go up by 12 volts. So we would say plus 12 volts, and then we'd come down by our unknown voltage here. So minus our unknown. And then we come down by 2 volts over there, so minus 2 volts. And then we get back to where we start. So we say that equals what? 0. Exactly. So that's 0 volts. Okay. So then if we wanted, we could sort of change the order here. We could say plus 12 volts minus 2 volts minus our unknown equals 0 volts. And then we could look at these and say, okay, 12 volts minus 2 volts, well, that's 10 volts. And then minus our unknown voltage equals 0 volts. So 10 minus our unknown thing is 0. Our unknown thing has to be 10 volts. Okay, so we could use that. We could use Kirchhoff's law in that way to figure out that we have 10 volts up there. Yeah.
So, since they're parallel, would you not be able to do the process where you take since they're the same,
Mhm.
you divide them by the number of resistors there are in parallel? Find the equivalent voltage? Or is that just resistance?
That's for resistance. Yeah. So yeah, if these were the same resistance values and we wanted to find their equivalent resistance, yeah, then we could take one of those resistance values and divide it by 2. Yeah. So that's a good reminder. Yep. So we could use Kirchhoff's law that way to find that we have 10 volts up there. Again, we could kind of see this by inspection. We know that we have 12 volts total, and so then we know that the voltage over here has to add up to 12 volts. Remember, it's kind of like building a tower with those blocks. We know that the tower is going to be 12 inches tall, so these things together have to add up to 12 inches over here. So we could kind of see that by inspection, but Kirchhoff's voltage law is a formal way of saying that. So, so are there questions about that? How we got it or what it means? No? Okay. All right. So those were Kirchhoff's 2 laws, Kirchhoff's current law and Kirchhoff's voltage law. So then, let's briefly review voltage dividers. So a voltage divider does just what it sounds like. It takes a power supply, so this is a voltage divider, really it takes a large voltage and it divides it among several resistors. So a voltage divider is nothing more than 2 or more resistors in series. And this can be very useful because sometimes you have a circuit and you want to take a large voltage and cut it into pieces, essentially, make it into smaller voltages. So, for instance, you might have 9 volts up here at the top. And if all of these resistors were the same value, let's say that they were all 1 kilo ohm, and 1 kilo ohm, then they would all get an equal share of that voltage. So they would each one is a third of the total resistance, so each one would get a third of the total voltage. So a third of 9 is 3, so you'd get 3 volts across there, 3 volts across there, and 3 volts across there. And so that would make the voltage relative to ground. So up here, the voltage relative to ground is 9 volts. So if we start there and we go down by 3, what would be the voltage at that point relative to ground? 6, exactly. 6 volts. And so then what would be the voltage at that point relative to ground? 3 volts, exactly. So this voltage divider took a 9-volt source and created a 6-volt source and also a 3-volt source from that. Okay? So we took our voltage and we divided it among these resistors. So questions about that? Okay, now that's if the voltages are all, or if the resistance values are all the same. If they're all the same, they get equal share of the voltage. Now, if they are different, then they get a proportional share of the voltage. So, so let's say we have voltage divider, and one of these resistors is 2 kiloohms, and the other resistor is 8 kiloohms. Okay? And we got ground down here, and let's say we have five volts up here at the top. Now we want to know how much voltage is across these resistors. Well, since these resistors are not the same, we can't just divide 5, in half. We have to use that other formula. So the other formula was, we said V1 equals V total times R1 over R total. Okay? So in this case, we can look at the voltage across this resistor. So we could say V1 equals the total voltage, so that would be 5 volts, times, and then this is R1 would be 2 kiloohms. And then what would be the total resistance for this circuit? 10 kiloohms, exactly, just 2 plus 8. So 2 kiloohms over 10 kiloohms. So that is 5 volts times, it works out to be 0.2 if we did that on the calculator. So that equals 1 volt. So we would have 1 volt across that resistor, and then the rest would be across this resistor. So how much would be down here? 4 volts, exactly. So, so when the resistance values are uneven, we have to use this formula up here. So questions about that? Okay. So this is another way of saying that the voltages are just proportional to the resistors. So 2 is a fifth of the total resistance, so it gets a fifth of the total voltage. So that'd be 1 volt. 8 kiloohms is 4/5 of the total voltage, so it gets total resistance, so it gets 4/5 of the total voltage. So yeah. So that's a quick refresher on voltage dividers. So questions about that? Okay. So then let's go on to our main topic, which is Watt's law. So Watt's law, really it's not so much a law as a definition. So Watt's law really just says that power equals voltage times current. And these are often abbreviated, so you would say P equals V times I. Okay? So that's what Watt's law is. That's all it is. It's just a simple formula, okay? Nothing tricky about it. So, but what is power? Well, power is really the amount of energy that a circuit is using at a particular instant, okay? It's how much energy is being used up at that particular point in time. And that could be a big complicated circuit like a computer, or it could be a really simple thing like a light bulb. You could find the power for either one of those things. Okay? So that's what power is. It's how much energy is being used at a particular instant. Now, this is really important in electronics because any circuit is using energy. So all circuits are using power. And that power can be going towards useful things that we like such as lighting up a light bulb or turning a motor or playing music out of speakers or running your cell phone or your computer. So there are a lot of useful things that power can do, or that energy can go towards, but it can also go towards wasteful things, which are mainly heat. Okay, so your circuit could be using a lot of power and just turning it into heat, which is generally wasteful. Now, sometimes that can be useful, like in a toaster oven. You want to create that heat, but oftentimes that heat is just waste. Like when you got a desktop computer and that computer is generating heat, that's just waste. It's not doing anything useful for you. Okay, so it's important to know how much power our circuit is using. First of all, it's important to know how much power any component is using, because we want to know how much energy our battery will be, supplying, and also how much heat will be created. Because if we have too much heat in a circuit, that can be detrimental. It's wasteful. It can even be dangerous, right? If your circuit gets really hot, it could actually burn you. That happens. If you plug in a component backwards, that can heat up and you can get seriously burned. So it's important to be able to look at a circuit and know how much power that circuit is going to use, whether it's for useful things or just heat waste. Okay. So we know what power is. It's just the amount of energy that's being used. We talked about why that's important. So let's talk a little bit about what Watt's law actually means. Okay? So we said that power is voltage times current. So power is the amount of energy that's being used in the circuit, and then we know that voltage is the electrical pressure, and then current is like the amount of electricity that's flowing. So if we want to understand why this formula is true, we could think about an analogy of a water wheel. So imagine an old-fashioned mill that's sitting by the side of a river, and the water, there's a giant paddle wheel that dips into this river. And the water from the river flows by and pushes this paddle wheel around, okay? So imagine that. Now, the speed that this paddle wheel is turning is the amount of energy that's being created at that point. Or you could think of it as the amount of energy that the river is using at that point to turn the wheel, okay? So the faster the wheel turns, the more energy is being used. So really it takes two things to make this wheel turn. You need to have pressure on it, and you need to have a lot of water flowing past. If you have just one of those things, this wheel's not really going to turn. Okay? Imagine you had a lot of pressure, but just a little tiny stream of water. You got a super soaker, you pump it up, and you squirt it at this paddle wheel. It might have a lot of pressure, but there's not enough flow to really make that wheel turn. Okay? Or conversely, if you have a lot of flow, you got a big, wide river going past, but it's moving, there's no pressure, so it's moving really, really slowly. It's also not going to turn that wheel very much. Okay? So pressure by itself isn't enough to make that wheel turn. Flow by itself isn't enough. You need to have both pressure and a large amount of flow. So you need to have a lot of water moving past there, and it needs that pressure to make it move quickly in order to turn that wheel. Okay? The same thing is going on with electricity. You need to have the voltage to push that electricity along combined with a large amount of current, and when you have both of those things together, that's when you get a lot of energy being used. That's when you have power, okay? So that's what Watt's law is really saying. power, the amount of energy is being used, is your voltage, your pressure times the current, which is the amount of flow. Okay? Bless you. So that's what Watt's law really means. So there are a couple of different ways to write Watt's law. Okay, so we can write it like this: power is voltage times current. But again, this is kind of like Ohm's law, where we have three of the different variables, and we might want to find, one of them if we know the other two. So if you are familiar with algebra, you could kind of rearrange these things, but a lot of people don't like doing that. So it's nice to have another form where you can find one or more of these things, or one of these things if you know the other two. So we can do that. So we have a form that's kind of like Watt's law. We write it like, or kind of like Ohm's law. We write it like this: P, I, and V. Okay? So, and we use it just like Ohm's law. So if you want to find power, you would just write down P equals, and you cover that up. You see that it's I times V. That's what we have. If you wanted to find current, you would write that down. You would say I equals, cover that up. You can see it's P divided by V. Or if you want to find the voltage, we write down V equals, we cover that up. We see it's P divided by I. Okay, so we can remember Watt's law in this form, and then if we want to find, if we know two of those things, we can find the other one. Okay? Also, there are two other forms of Watt's law that are sometimes helpful. So we can say power equals I squared times R, or we could say power equals V squared divided by R. Okay? So these can be helpful if we know, say we know the current and the resistance and we're trying to find power, or we know the voltage and the resistance and we're trying to find power. Okay? So these are all different forms, all different ways of writing the same thing. Okay? Really, this is Watt's law. These are just all different ways of writing that. Okay? And fortunately, this is kind of a lot to remember, but fortunately there is a chart on page 57 in the lab book. And that kind of summarizes everything that I've just written up here. And it ties in with Watt's law also. So if you want to take a look on page 57, we've got a circle, okay? So we got this circle, and in the middle, we've got four things that we might want to find. We've got voltage, current, resistance, and power. Okay? And then around the outside of the circle, we have the different ways of finding these things. So for instance, over here on voltage, we can see that voltage is P divided by I, or you could also say that it's the square root of P times R, or you could say that it's I times R. Okay? So say we wanted to find voltage and we know the power and the resistance. Well, we could look over here and we say, okay, I want to find voltage, so I'm going to look in this quadrant. I know power and resistance, so I'll use this formula. Voltage is the square root of power times resistance. Okay? Or if I'm trying to find voltage and I know the current and the resistance, I can look over here and I can say voltage is I times R. Okay? So this circle can be a helpful way of figuring out what you want to know. Okay? So let's do an example here. So let's say that I have a power supply and I've got a resistor over here, and I know that this resistor is dissipating, say, 25 watts of power, and I know that there is, say, 2 milliamps of current flowing through that resistor. And I want to find the voltage across this resistor. Okay? Well, what I can do is I can come over here to my circle and say, okay, I'm trying to find voltage. So I write down V equals, and then I look at the information that I have to try and figure out which formula I'm going to use. So over here, I know current and I know power. So I have to come over here and find a formula that, for voltage, that includes current and power. So what would be my formula to find my voltage then?
P over I.
Yeah, power over current. So I know I'm looking for voltage, and this is the formula that includes power and current. So I would say voltage is P divided by I. So then that equals, the power is 25 watts. And then the current is 2 milliamps, 0.002 amps. So what does that come out to be?
12.5 millivolts. 0.0125.
I think it's going to be big, because it's dividing by a small number. So I think it'd be 12.5 thousand.
Yeah, 125.
So
Yeah, 12.5.
yeah, so 12,500 volts. Wait. Something doesn't seem quite right. I guess that's it. So anyway, yeah, so that's how you would use that formula, okay? Yeah, so any questions about that?
Can you show like one more demonstration?
Yeah, for sure. So another thing that we might want to look at is we might want to think about some of those resistors we have in the back bins back there. So those resistors, most of those resistors are 25 or quarter watt resistors. So they can handle 0.25 watts, okay? So So imagine that we have a 1 kilo ohm resistor, and it's handling, it can handle up to 0.25 watts, and we want to know, so how much voltage can we put across that resistor? So we look over here, and here we know we're trying to find the voltage. We know the resistance and the power. So then the formula would be V equals the square root of power times resistance. Okay, so in this case, that would be the square root of the power is, so 0.25 watts times 1,000 ohms. So that would be the square root of 250. So what does that come out to be?
50.
Not quite. Somebody have a calculator? 15.8. Okay, so 15.8 volts. So we would want to have a maximum of 15.8 volts across this resistor. If we put more than 15.8 volts across that, then it would start to heat up. Okay.
How is that 250? Then
So that's
5,000.
0.25 times 1,000.
0.25.
Yeah, yeah. So yeah, they're a quarter watt resistors, so 0.25 watts. Yeah. But, so that's for a 1 kilo ohm resistor. Now let's see what happens when we have a we go into the same bins, but now instead of a 1,000 ohm resistor, we pull out a 100 ohm resistor. Still 0.25 watts. Okay? So we can use the same formula, V equals square root of power times resistance. So that would be the square root of 0.25 times 100. So that would be the square root of 25. So what's that?
5.
5. Yep. So 5. So for a 100 ohm resistor, we can only put 5 volts across it before it starts to get destroyed. Okay? So a lot of our experiments, have voltages that are higher than 5 volts, right? We work with 12 volts or 15 volts or even 20 volts sometimes. So if we were to put any more than 5 volts across one of these 100 ohm resistors, that would start to get really hot and maybe even burn you or start to smoke, okay? And if we did the same thing with a 10 ohm resistor, so then it's still 0.25 watts. All of these back there, most of them are 0.25 watts. So then with that one, the voltage would be the square root of 2.5. So that would be about 1.5. So for a 1.6. So for a 10 ohm resistor, you can put less than 2 volts across it, about 1.6 volts across it, okay? Before it starts to overheat. So when these resistor resistances go down, their ability to handle voltage also goes way down, okay? So this has happened to people in this class before. They pull a resistor out of the bin, and they're used to working with 1 kilo ohm resistors that, can handle 16 volts across them. They take a little resistor, like say a 10 ohm or maybe even a 1 ohm resistor, and they put it in their circuit, and they put 5 volts across it. All of a sudden it gets really hot and starts to melt things and maybe burn them, all right? And the reason is because the smaller the resistance is, the less voltage it can tolerate, okay? So, questions about that? Okay, so again, the circle in your book has these little quadrants filled in for all of the different sections. I'm not going to take the time to draw it all out on the board here because you have it in your lab book, but this can be very useful for figuring out what you have, one of these values if you know the other information about your circuit, okay? All right. So any questions about Watt's law or about this chart in your book? Okay. All right. So now for something completely different, okay? Now we're going to talk a little bit about rounding, okay? So rounding is simply the process of making approximations, making the best approximations we can when we have more information than we need. So imagine you've got a measurement, and you say, you're taking this measurement and it comes out to be 12.7 volts. And you decide, okay, well, that's 3 digits of information. I really only care about 2. Okay? I really only want to keep 2 of them. I want to get rid of one of those digits. So sort of the simplest thing to do would just be to get rid of that last digit. So we could say that's kind of like approximately, 12 volts, right? We just dropped that last digit. But that's wrong. That's not the right thing to do, okay? Because if we're gonna keep only 2 digits, we want to make sure that they're the best 2 digits that we can, okay? So what do I mean by that? So imagine you got this number line, right? We're starting at 0, 1, 2, 3, 4, 5, 6, yeah. So it goes on, and you make your measurement. Well, on that number line, your measurement is going to be, it's 12.7, so that's somewhere between 12 volts and 13 volts, okay? And if we're only going to keep 2 digits, we want to keep the 2 digits that are the best representation of our measurement. So 12.7 volts is somewhere like that. So you can see it's actually closer to 13 than 12. So if we have 12.7 volts and we want to just keep 2 digits of information, we would say that's actually approximately 13 volts, okay? Because it's closer to 13 than 12. So that's what we're trying to do with rounding. We're trying to look at a number, get rid of some information, but keep the best approximation that we can, okay? All right. So the basic procedure for this is you decide how many numbers you want to keep. You look at the last digit, or the digit to the right of the last one that you want to keep. And then if the number is 5 or greater, you round up. And if it's 4 or less, you round down, okay? So in this example, we want to keep 2 digits. So we would look at the third one. That's greater than or equal to 5. And so this number rounds up. So it goes from 12.7 to 13, okay? So that's the general procedure that you use. You decide how many digits to keep. You look at the digit to the right of the last one that you want to keep. 5 or greater rounds up, 4 or less rounds down. Okay? So let's do a couple of examples. So let's say we have 1.3 and we want to keep only one digit here, okay? So what we would do is we would look at the number after, the digit after the one we want to keep. So we look at that. We see that it's 4 or less, so that rounds down. So what does this become?
1.
1, exactly. So that's 1, okay? If we look at 4.8 and we want to keep one digit, we look at that. That's 5 or greater. So what does this become?
5.
Yeah, it rounds up, it becomes 5, okay? If we look at 9.5, we would look at this number. It's 5 or greater, so it rounds up. So this becomes approximately 10, okay? So that's if we wanted to get rid of these decimal numbers and end up with a number that had no decimals. But we can also do this with a certain number of decimal digits, okay? So say we have a number that's 1.2647, and we wanted to keep 3 digits after the decimal. So what number would we look at to see if we round up or round down?
7.
Yeah, we would look at this 7, and then so that rounds up, so then that would become approximately 1.265. Okay, it rounds up, so it makes this number go up 1. Okay. If we looked at the same number and we wanted to keep only 2 digits after the decimal point, what number would we look at to see if we round up or round down then? Yeah, the 4. So we would look at that one. So does that round up or down?
Yeah.
Down. So then what number would I have over here?
1.23.
Yeah, exactly. 1.26. Okay? So this is, 3, so we wanted to keep 3 decimals. In this case, here we wanted to keep 2 decimals. If we wanted to keep just 1 decimal, and we looked at 1.2647, then we would look at this 6 here. We would see that that rounds up, so that becomes 1.3. And if we wanted to keep no decimals, then we would look at the 2, that would round down, and then that would be approximately just 1, okay? So any questions about that? Okay. So one of the things that students often ask is, how many digits should I keep when I round a number? Okay. Say I'm doing my lab experiment. How many digits, how many decimals should I keep when I'm doing my experiment? And unfortunately, there's no set answer on how many decimal digits you should keep. And let me explain why, okay? Imagine that you had a small number, like, 0.00135 amps, okay? We see that kind of number a lot. That would be 1.35 milliamps, right? And that's a fair number to have in your circuit. Imagine you rounded that to 2 decimal points, just 2 decimal digits. So then what you would get is that you would say 2 decimals that would just become 0.00 or 0. We would say that if you're just keeping 2 decimals, that would just be 0, okay? And for a lot of circuits, that's not precise enough. If you have 1.35 milliamps, you want to know that there's some current flowing. That's not the same as 0, okay? But now imagine you had a really big number. So imagine you had a number that was like 1,587,628.65372 ohms, okay? If you kept 2 decimals with that, then you'd have to keep all of this information. You'd still have to write down, a whole bunch of numbers. 1,587,628.65. Okay, so you'd still have to keep a whole lot of information. So up here, 2 decimals was not enough information. Down here, 2 decimals is too much information. Okay, so that's the reason why we can't just specify a certain number of decimal digits that we have to keep in every case. What we do instead is we keep a certain number of digits of information. Some people might have heard this called significant figures. Okay, they're the information that's significant about this this number. Okay, so generally, when we're writing an answer, we want to keep 3 significant figures. Okay, and so a significant figure is if you're talking about a number that's greater than 0 or greater than 1, it's the first first digits in that number. If you're talking about a decimal, so let's look at 3 significant figures here. 3 Okay, so in this case, that would be the first 3 numbers. So then we would look at the 4th number and decide whether we round that up or down. So in this case, that would be 7. So that would round up in that case. So then that just becomes 1,590,000. Okay? So we end up with 3 significant numbers, 3 significant figures at the beginning of our approximation. Okay, so okay, up here, if we wanted to keep three significant figures, the significant figure is when the number is a decimal, the significant figure is the first number after the decimal point that's not a 0. So in this case, we just ignore the zeros. The three significant figures would be these three numbers. So this would be approximately 0.00135. So there would be no change. We would keep that whole thing because all of these are, we want to keep three significant figures, and those are the three significant figures, okay? So and hopefully you can see that in this case we're retaining kind of the same amount of information from this number up here as we are from down here. So we have 3 digits that tell us information about this number. We have 3 digits up there that tell us information about that number. Okay, so that's usually a good way of judging where to round. You keep 3 significant figures. Another way to think about that is that your rounding will change your answer by less than 1%. So your answer, you're not going to be throwing away more than 1% of your information. Okay. So that's a good way to round. You want to generally, for this class, 3 significant figures is a good number to keep. Okay. So questions about that? Okay, so that's how we do rounding. We want to keep 3 significant figures, so we look at the 4th digit after that, and then we decide whether to round that up or down. Okay? All right. So that was all that I wanted to say about for the lecture. So do you have any questions about anything that we talked about in the lecture today? Okay. All right, so then let's go on and do a preview of today's lab. Okay, so today we're going to be doing the Watt's Law and Power Lab, and that starts on page 93 in your lab book. So the first part of the lab is going to be in multisim, and you're going to be working on this circuit. So in this circuit, we have 3 virtual meters. So we have this one here, which is XMM1, this one over here, XMM2, and XMM3 up there. Oh, this is XWM, I guess, XWM1. Anyway, let's look at this meter here, first of all. So this meter is measuring from one side of a resistor to the other. So what kind of measurement do you make when you're measuring from one side of a resistor to another in a circuit? What's that? Yeah, this would be voltage measurement. Remember, voltage is non-destructive, and it's measured from one side of the resistor to the other. You could also say that this meter is in parallel with this resistor. So when you put the meter in parallel with the resistor, you can measure voltage that way. Now let's look at this meter over here. Over here, the wire flows out of our resistor, and then it eventually connects over to this meter here, and then from that meter it goes on. That meter goes on and connects back to the other side of our power supply. So, so in this case, we've connected the meter in series with our resistor. So what kind of measurement do you make when the meter is in series with your resistor? Current, exactly. Remember, we have to break the circuit apart and insert the meter to measure current. So that's what we have here. This meter is in series and it's measuring current. Okay? So we have this voltage meter that's in parallel and a current meter that is in series. So now let's look at this meter up here. Up here, we have two wires that are connected across this resistor. So part of this meter is measuring in parallel with this resistor. And then we also have another wire that goes into this meter and continues on. So another part of this meter is in series. So one part of this meter is in parallel and the other is in series. So it looks like this meter is measuring voltage in parallel and series, it's measuring current. And in fact, if we look very closely at that illustration, we can even see that the left side of that meter is labeled with a V for voltage and the right side is labeled with an I for current. So this meter is measuring both voltage and current. So what do you think it would be doing? What could it do if it was measuring both voltage and current? What else could it tell you? The power, exactly. So this is a power meter. It measures voltage and it measures current. And then, what law do you think it uses to calculate the power? Watt's law, exactly. So this meter is just measuring voltage and current and then multiplying them together, like Watt's law says, to tell you the power. Okay, so this is a power meter. So, and it calculates that power by measuring the voltage and the current. Okay, so what we're going to do is we're going to run this circuit and do some simulations here. So let's open up that circuit here in Multisim. So that will be under File Explorer, and we'll go here to Instructor Files, and then ET302, and then this is under Watt's Law, Power Lab. It's just under Power Lab, I'm sorry. And then this is the first circuit here. Okay, so this is the same circuit that we saw in the lab book. And then the lab book, this has a table here. So it asks you to write down the voltage, the resistor voltage, and then the current. So if we run this simulation, we can run this simulation, and then we can look at the voltage here. So that would be 10 volts, and then the current is 10 amps. So we would come over here to our table, and we would write down the voltage is 10 volts, and then the resistor voltage is 10 volts. The current is 10 amps. So then what would be the voltage times the current? Yep, 10 times 10 is 100. Yeah, and voltage times current gives us watts. So V times I would be 100 watts. So we calculate that there should be 100 watts in this circuit. And then we can check it using this other meter, this power meter. So if we open that up, sure enough, it shows that this circuit is using 100 watts right now. Okay? So that's what you're going to do. So you just go through this table and you'll fill in all those values there. you'll change the resistor each time and get different values, and then fill in that table there. Yeah.
The meter power is the watts?
Yeah, the meter power is the reading that you get from this watt meter in Multisim.
Is that the one that says like, oh, it says like right below like 100 watts, like the, or the, right below the 100 watts?
Yeah, that's this meter right here, this one.
1,000, right?
No, that's actually 100. The numbers are a little bit small. It might be hard to read, but that's 100.000.
That's it, right?
Yeah, 100. Yeah. Yeah. I wish I could make this meter a little bit bigger, but I don't. I can make the meter bigger, but it doesn't make the number any bigger. So I apologize for that. Yeah. So that's what you're going to do. You're going to go through and change the resistor value and then fill in that table. Okay. And hopefully your voltage times current calculations will match up with the meter power in the simulation. And then the next part, you're going to use Watt's law, but you're going to use this other form of it, this I squared times R equals power form. So that'll be the Watt B circuit. So you'll open up that circuit. And then, so you can see it's almost an identical circuit. But here you're going to write down the current value, and then you're going to calculate I squared times your resistor. And then you'll compare that calculation to your meter power. And then down here, you have a very similar circuit, again with the watt meter. But here you're going to look at the V squared divided by R form of Watt's law. So you'll write down V squared, you'll write down your V squared over R, and then you'll compare that to the meter power. Okay? And then down here, we're going to look at power in a lamp board. So you're going to actually build this on, you're going to use those lamp boards that we have seen before, and you're going to build this circuit. So you're going to connect two of the lamps in parallel, and you're going to apply 12 volts. And then you're just going to do what it says here. So you're going to find the voltage across lamp 1, voltage across lamp 2. You're going to measure the total current and just do the calculations that it shows here to find the power that's being used by this circuit. Okay? So you're going to use this to find the total power, and then you're going to find the power for lamp 1 and lamp 2 and see if the power for lamp 1 plus the power of lamp 2 is the same as your total calculated power. Hopefully it should be pretty close. Okay. And then down here you're going to look at Watt's law with a resistor circuit. Okay. So you're going to build this on a breadboard. You're going to have a power supply, the current meter, and then the voltage meter. And then, yeah, you're going to do the measurements and calculations that are shown down here to find the power for that. Okay? So, yeah, and then that's just formulas. So this part that we just talked about is the end of the lab. So are there any questions about that? All right, then I will take attendance and let you get started.